Hi everybody, this is our lecture on section 3.7 on improper integrals. So the standard form of an integral is, right, the integral from a to b f(x) dx, where f of x is continuous on the interval from a to b. An improper integral is when you loosen, one of two conditions. One of these two conditions. Integral from a to b f(x) dx, where f of x has some discontinuity. In the interval from a to b, typically at a or b itself. Typically at x equal a or x equal b, but not necessarily. Okay, so that's one. Two, integral from like a to infinity. So a and b are not finite anymore, where f of x is continuous. So integral from a to infinity, or integral from minus infinity to b, or integral from minus infinity to infinity f(x) dx. So something like that. So normally you consider a finite interval from a to b, right? But here one of the endpoints is infinite, although the function is still continuous. Right? Whereas in the first example, you loosen the requirement of continuity, but you leave a and b finite. I mean, of course, you could have integrals that do both, but typically not. Not what's considered. So the question is, how does one deal with an integration problem of that sort? Because the definition of the integral is for the definition of the integral and the fundamental theorem of calculus, as we know it. There's more general fundamental theorem type things. But the fundamental theorem of calculus and the definition of the integral, the definition of the integral requires a finite interval, because you always have this delta x equals b minus a over n. And, if one of these guys is infinity, that just doesn't make sense. It's infinite. Or it requires continuity in the fundamental theorem of calculus. Okay, so how do we deal with that sort of thing? And it's not quite so hard. So first type. Okay, the integral from a to infinity f(x) dx is defined to be, so we define the integral from a to infinity equal to the limit as t approaches infinity, integral from a to t. Right? So the integral from a to t, that's all defined because t is a finite number. So you just get an answer for this in terms of t, and then you let t go to infinity. And that's the way we define that. When the limit exists, we say that the integral converges when the limit is infinity or does not exist. We say that the integral diverges. Alright, so converges and diverges. Converges mean you actually get an answer. Diverges, it's infinite, or the limit doesn't exist. Okay, so similar types. The integral from minus infinity to b, fx dx. Right, that's going to be defined as the limit as t goes to minus infinity, integral from t to b, and the integral from minus infinity to infinity, you define it to be the integral from 0 to infinity plus integral from plus the integral from minus infinity to 0. Okay, so you don't handle both these infinite limits simultaneously. You you define it as the integral of these two. This improper integral is defined as the sum of these two: the integral from 0 to infinity, and the integral from minus infinity to 0. Okay. So let's take an example. Okay, for example, we'll do the integral from 0 to infinity, 1 over 1 plus x squared dx. So if you were to draw the graph here, excuse me, the graph of this function looks kind of like that. So we're talking about this area here is what's being calculated. Alright, and that area is trailing out to infinity, even though the area is going to turn out to be finite. So this is the limit as t goes to infinity. Integral from 0 to t, 1 over 1 plus x squared dx. Antiderivative is arctangent x. So arctangent x evaluated from x equals 0 to x equals t. So we're still working on the integral. We're trying to get the integral as an answer in terms of t. Alright. So this is equal to limit as t goes to infinity, arctangent of t minus arctangent of 0. Well, arctangent of 0 is just 0. So it's the limit as t goes to infinity, arctangent of t. And what is that limit? Well, the arctangent function, right? So this is the function whose area we're calculating, but the graph of the arctangent function, right, has a horizontal asymptote at pi over 2, just like the tangent function has a vertical asymptote at pi over 2. So that's y equals arctangent of x, or t, I guess. Arctangent of t, this is the t-axis, that's the y-axis, and this is the vertical or horizontal line at y equals pi over 2. So this limit is equal to just pi over 2, And so that is the value of the integral, which is the area, shaded area shown here. Okay, so arctangent of t equals pi over 2, so the integral converges because you got an answer. It's not that you didn't get an answer or that the answer was infinite. Alright, let's try another example. This example you'll see a lot in ordinary differential equations class in dealing with what's known as Laplace transforms. So it's a type of integral that looks like this. Integral from 1 to infinity, some function, well it's fx e to the minus x. Okay, so it's an integral of this sort, fx times e to the minus x. Essentially, like the e to the minus x, that's a very small, it's a very fast dropping function to 0. So it essentially forces, all these functions f of x to go to 0. So here we're just doing x e to the x, e to the minus x. So this is the limit as t goes to infinity. Integral from 1 to t x e to the minus x dx. Now, in order to get the antiderivative here, okay, we'll need to use integration by parts. So I'm going to do the antiderivative down here, just as a side calculation, so as not to sort of mess up this progression too much. Okay, this can often be helpful in doing things this way. So we have a polynomial times an exponential function. So du is dx, and v is the antiderivative of e to the minus x, which is minus e to the minus x. Alright, so we got u times v minus x e to the minus x plus v du. Integral v du. So minus x e to the minus x plus antiderivative e to the minus x. So this is equal to minus x e to the minus x, and then the antiderivative e to the minus x again is minus e to the minus x plus c. So there's that antiderivative. So I'm just going to take that antiderivative and plug it into my calculation up here. So this is the limit as t goes to infinity. Minus x e to the minus x minus e to the minus x evaluated from x equals 1 to x equals t. So we're still working on that integral. We haven't done anything with the limit yet. So the symbol just keeps following us around for now. One moment. Okay, so evaluating this between 1 and t, we have minus t e to the minus t minus e to the minus t, and then minus evaluating this at 1 or at 0. I wanted that to be at, no, I can do it at 1. Do it at 1. Let me see. We need a little more space here. Okay. So now when I subtract it, these are just going to become pluses. Plus e to the minus 1 plus e to the minus 1. Alright, let's rewrite this. Let's factor out minus e to the minus t. Minus e to the minus t, and then this just becomes t plus 1. Right, plus, and these are just constants, 2 over e. And I have 1 over e plus 1 over e gives me 2 over e. E to the minus t, of course, is 1 over e to the t. Right, plus 2 over e is just a constant. Alright, this limit, right, this is the infinity over infinity variety, or indeterminate form. Alright, so this is infinity over infinity. So we can use L'Hospital's rule. Right, and it becomes the limit as t goes to infinity. Derivative of the top is minus 1, derivative of the bottom is just e to the t. Right, and then, I mean, we've separated this a while ago. It's just a constant, so we're not working on that anymore. All right, but now this is 1 over infinity, so that's 0. Okay. So, you know, that's a pretty nice problem. Okay. All right. Let's see. Another example. And I'm not actually going to do the calculation here, but I'm just going to write it down. Okay, you can check this on your own. Do the following as an exercise. Oh, I should say, so the integral here converges. All right, do the following as an exercise. The limit as t goes to infinity, the integral the integral from 1 to infinity, 1 over x to the p dx. So show that this converges for p's greater than 1 and diverges for p's between 0 and 1, including the 1. All right, so this integral converges for like p equal to 2, 1 over x squared, or 1 over x to the 3 halves, whatever it might be. Okay, x to the 1.01. Okay, that integral is going to converge as long as p is bigger than 1. And the integral diverges for p's less than or equal to 1. Okay, so do that as an exercise. Show that that's the case. Okay, it's a good practice problem. All right. Now, that's an important improper integral because it allows us to do comparisons. So here's the comparison test. It states the following. Suppose that 0, so f of x is a non-negative function, and g of x is at least as big as f of x. So for all x bigger than or equal to a. Alright, then you get this picture. So here's a, and there's f of x, or we'll say that's g of x, and then f of x is somehow below it. You might touch it from time to time, but it's below it. And it's bigger than 0. Okay, so that's f of x. Well, in this case, I mean, clearly, the area under the curve for x is less than or equal to the area under the curve for g. So the integral from a to infinity of f of x is less than or equal to the integral from a to infinity of g of x, I forgot my dx. And it's bigger than or equal to 0. It's going to be a non-negative answer. Okay. Now, a couple things you can notice about that is the following. One, if the integral from a to infinity of fx diverges, so the integral for f of x is going to exist. That limit is going to exist. The only problem is it might be infinite. Right? There's no problem with the thing jumping between something positive and something negative. It's just a strictly increasing function, this integral. I mean, as t goes to infinity, the area just keeps increasing. So if this doesn't exist, it means, because the limit governing this integral is infinite. So if the area under f of x is infinite, then certainly the area under g is infinite as well. And 2, if the integral from a to infinity of g of x, the bigger one, is finite, well, if that converges, then the integral for f Okay, so if the area under G is finite, then the area under F, which is positive, must be finite as well. Okay, so comparison tests are nice for trying to tell if some improper integrals converge or diverge. Just converge or diverge. You're not actually trying to calculate them. You just want to determine convergence or non-convergence. Okay. So the thing you usually compare to is integrals of this sort, 1 over x to the p. So that can often be a comparison that will give you what it is that you're looking for. So for example, okay. So determine if this integral 1 over x to the third plus 1 dx converges or diverges. Okay, we're not asking if it converges. What does it converge to? We're not asking to calculate it precisely. Just asking, does it converge or does it diverge? Okay. Well, certainly 1 over x to the third plus 1 is positive when x is positive. Okay, since we're doing x's from 1 to infinity. Okay. Okay, also, because x to the third plus 1 is greater than x to the third, we get that 0 is less than or equal to 1 over x to the third plus 1 is less than 1 over x to the third, right? As the denominator gets bigger, the fraction gets smaller, right? Therefore, because the integral from 1 to infinity, 1 over x to the third dx converges, right? In this example, 1 over x to the p, the integral from 1 to infinity, that converges for p's bigger than 1 and diverges for p's less than or equal to 1. So here we have p equal to 3, which is bigger than 1. So now, because the integral for this function converges and this function is less than that function, it must be that we get that the integral from 1 to infinity, 1 over x to the third plus 1 dx converges as well. Right? The integral for the larger function converges. This is the larger function, it converges. Therefore, the integral for the smaller function must converge as well. In other words, the area for the smaller function can't go out to infinity and can't jump between positive and negative. It can't not exist. Okay? So this area under this curve is finite because the area under this one is finite. Alright, so that's comparison tests. Alright, so that's the first type of improper integral that I wish to discuss, right? And we mentioned two different types. Right, the first type, well, I mentioned it second here, but the first type is the integral from a to infinity fx dx, or minus infinity to b fx dx, or minus infinity to infinity, where f is still continuous. Now we want to discuss the type where you have the integral from a to b where f of x is not continuous. Okay, it's discontinuous at some point, typically at the end point, a or b. Okay, so let's discuss that type. So given f of x continuous on a less than or equal to x less than b, but discontinuous at b. So something looks like this, right? You have your interval from a to b, and the function is all nice and continuous, except at b, it goes off to infinity, or something like that. I mean, there's different things it can do to not be continuous, but typically we think of this as infinite discontinuities. Other types of discontinuities are less difficult to deal with. Jump discontinuities and removable discontinuities are easy to deal with. Infinite discontinuities like this, well, those require this technique that we're talking about here. So we want to measure, this area here. So how do we do that? Okay, so here we define the integral from a to b of fx dx. So you use a limit approach again. It's the limit as t approaches b on the left. Integral from a to t fx dx. So that's when you have the discontinuity at b. You could have the discontinuity at a instead. So So let me copy this over one more time. Alright, given f of x continuous on a, the interval from a to b, but not continuous at a. Alright, here we define the integral from a to b f(x) dx equal to, well, the trouble point there is a, so you set up your limit for a. So it's the limit as t approaches a on the right, integral from t to b f(x) dx. And then c, if f of x is continuous on a less than or equal to x less than or equal to b, except at some point in the middle, c between a and b, then we define the integral from a to b f(x) dx equal to the integral from a to c plus the integral from c to b. Thank you. So in this manner, we have put the discontinuity at the end of the integral again, so we can use the techniques of a and b at that point. Right? So this is like a function that looks like this. So a, b, and then there's some troubling spot c in the middle, and the function maybe is climbing up the asymptote in different directions. When you're trying to calculate the area here. So you calculate those areas separately. You calculate the area on one side of the discontinuity, and then you calculate the area on the other side of the discontinuity. And again, if these limits exist, then we say that the integral converges. Otherwise, the integral diverges. Alright, same. Oh, if the limits exist, then we say that the integral converges, exists, and is finite. Exists and is finite. Then we say that the integral converges. Otherwise, if the integral is finite, is infinite, or the limit just doesn't exist, then we say that the integral diverges. Okay. So let's take a look at some examples for that. The integral (1 over square root 4 minus 2x). So this one's fine everywhere. right? Everywhere that this is positive, right? The place that you run into trouble is where, the bottom might be equal to 0. Right? I mean, as long as the inside of that integral is going to be non-negative, you can take the square root. Except because you're on the bottom of the function, you can't have it equal to 0. Right? So the troubling point is at 2, and at numbers less than 2, this integral is going to be, or the thing underneath here is going to be positive. So we'll say the integral from 1 to 2, something like that. Okay? So this is continuous everywhere except at 2. At x equal to 2. So we set this up as a limit. Right, so t approaches 2 from where? From the left or from the right? Alright, so the interval looks like this. Alright, here's 1 and here's 2. So we're approaching 2 from the left. Right, from numbers less than 2. Integral from 1 to t, and we'll write this as 4 minus 2x to the negative 1/2 dx. Alright. In order to calculate this, I'm going to have to do a u substitution. So why don't we do the antiderivative separately, just like we did in that previous problem, and then we'll plug it back into this main calculation here. So as to not clutter things up too much. So we want to do the antiderivative of 4 minus 2x to the negative 1/2. So I'm going to let u equal 4 minus 2x. So du is minus 2 dx. So minus 1/2 du is dx. So this is equal to antiderivative u to the negative 1/2. Negative 1/2 du. Alright, so this is move this over here. This is minus 1/2 times the antiderivative u to the negative 1/2 du. Antiderivative of that, so add 1 to negative 1/2, you get positive 1/2, reciprocal is 2. So positive 2, so I have minus u to the positive 1/2 plus c. So this is equal to minus square root 4 minus 2x plus c. Okay, so there's that antiderivative. So let's plug that antiderivative up into this main calculation over here. So this is, right, so because I got all these like limits and other things going on, so to drag all that stuff along while I'm trying to do this calculation, it makes things kind of messy. So now that I know what this antiderivative is from first to last, I can do things a little bit more neatly. So it's a limit as t goes to infinity, limit as t goes to infinity minus square root 4 minus 2x from 1 to t. So this is a limit, or not t goes to infinity, t goes to 2 from the left. Limit as t goes to 2 on the left, minus square root 4 minus 2t plus the square root 4 minus 2. This one is equal to just square root of 2. This one, well, as t goes to 2 on the left, this just goes to 0. Right? We can just plug in t equal to 2 because this function is actually continuous at 2. So we can just plug in t equal to 2 and you get 0. Alright, so that one is 0 plus root 2, so the answer is root 2, so the integral converges. Okay, how about this? How about this example? So, integral from minus 1 to 1, 1 over x squared dx. Alright, this one is continuous everywhere except at x equal to 0, where you have this infinite discontinuity, and the function looks like that. Actually, I drew too much. There we are. Alright, so this is y equals 1 over x squared. Alright, starting here and here. Alright, so we're looking for this area here plus this area here. Well, you'll notice that those two areas are, geometrically the same. One is just a reflection of the other. Right? So, because that discontinuity is in the middle, you write this as the integral from minus 1 to 0 at 0, 1 over x squared dx, plus the integral from 0 to 1, 1 over x squared dx. But they're the same, really. So it's the integral from 0 to 1, 1 over x squared dx. So this is equal to the limit as t goes to 0 from the right. Right, because we're working with numbers bigger than 0. Numbers between 0 and 1 are bigger than 0, so you're approaching 0 from the right. Integral from t to 1, 1 over x squared dx, antiderivative of 1 over x squared. Right, 1 over x squared is x to the minus 2, so the antiderivative is minus x to the minus 1. So it's minus 1 over x from t to 1. So this is the limit as t approaches 0 from the right. So at 1 you have minus 1 plus 1 over t. But as t goes to 0 on the right, this is infinite. So the integral diverges. Okay? And it's kind of interesting to note the integral from 0 to 1 of 1 over x to the p, right, this converges for 0 less than p less than 1 and diverges for p bigger than or equal to 1. So it's exactly the opposite scenario that we had for the integral from 1 to infinity. So whereas, so let me copy it and paste it there just for comparison. Got it up here somewhere. There it is. Well, I'll just copy that and put it underneath, whereas this integral converges for p's bigger than 1 and diverges for p's less than 1, less than or equal to 1. So when p is equal to 1, it diverges in both instances. Okay, but other than that, you get the exact opposite result. Here you have convergence for p less than 1, and here you have convergence for p's bigger than 1. So that's kind of neat. Okay, so that is the lecture for this section, 3.7.